In yesterday's class, we have started with the concept of gravitation. So let's continue the discussion from there. In yesterday's class, we have seen with the universal law of gravitation, then what is the idea of gravitational field. And we found that the gravitational field is on Earth, okay, or the gravitational field due to Earth is nothing but the acceleration due to gravity g bar. Acceleration due to gravity g bar. So this was the idea of gravitational field. Clear? Now today gravitational potential is nothing but, let's say you have a block of mass m, clear, which is held at rest, which is held at rest. Now let's say you want to bring a block of mass m. You want to bring a block of mass m. Okay. In fact, not exactly mass m. You want to bring 1 kilo of mass. Clear? You want to bring 1 kilo of mass and place it at a point P, which is at a distance of r from the capital M. Place it at a point P, which is at a distance r from capital M. So definitely, what will be happening? You see, we know that these both of them will be attracting each other. Clear? So I can call this as if this is Fg bar, clear, force due to gravity. In fact, here because it's 1 kilo of mass, let's say this is the electric field, and this is a minus electric field. Clear? So definitely there is some electric field acting on it. That means definitely there is some force times electric field acting on it. That means definitely there is force, there is displacement. That means there must be some work done. Clear? So,
Yes, sir.
so gravitational field is defined as the work done by external agent. Work done by external agent in moving, in placing, in bringing and placing a unit mass at point P from infinity. That means from infinity you are bringing it and placing it point P in the presence of mass m, or in the presence of electric field, in the presence of mass m, or in the vicinity of mass m. Clear? So that is nothing but the work done. That means work done in bringing a 1 kilo of mass from infinity. Let's say assume that this was infinity. From infinity you are bringing it and placing it over here. So this is the idea over here. Now for this what we can do is that we know that work done by external agent per unit mass, right? Work done by external agent per unit mass. So we know that the small work done will be equal to how much? We know that that is F bar dot S bar, F bar dot ds bar, F bar dot ds bar. Now here let's assume that you are pushing this by a distance of dr through the, you're pushing this by a distance of dr uh, towards the mass. Here let's say this was the initial position. You see, this is a final position P. Clear? This is a final position P. Let's say this was the initial position M and O. Okay, this was at position O. Now you have moved it to a point P. Clear? By a distance dr in this direction. Now where is the direction of the external force? In this case, because gravitational field, force due to gravity is towards the center, what we can say? We can say that the work done by external agent will be how much?
E bar into dr bar.
So that will be F external, because electric field is trying to act inside. So we can say, or what what shall we do? Shall we calculate the work done by the gravitational field? And then we say that because this gravitational force, we know that it's a conservative force, right? So we can say we can calculate the work done by gravity and say that delta is equal to negative of external force, or we can directly calculate the value of the external force. Clear? So here, let's assume that the value of the external force is towards right. So here that's the that was supposed to be the electric field. So let's say this is the value of the external force, F external. Clear? So that means if I'm interested in calculating the external work done, clear, this is nothing but external work done. Now we know that external work done is nothing but force due, negative of force due to gravity dot ds bar. Is that right?
How, sir? How is it the
Yes,
negative
sir. How
of?
is it?
At any instant, kinetic it is moved in such a manner that provided slowly, bringing and placing, yes, slowly. We forgot the word slowly, but slowly. That means instantaneous kinetic energy at any instant. Kinetic energy at any instant is zero. Understood? If there is no kinetic energy, that means acceleration is zero. Clear? The kinetic energy, instantaneous kinetic energy is zero. That means, you see, look here, look at the argument here. Instantaneous kinetic energy is nothing but half m v instantaneous square is equal to zero. That implies acceleration instantaneous is equal to zero. That means F net force is equal to how much? Zero. Right?
Yes, sir.
There are only two forces acting, that is external force as well as gravitational force. Gravitational force is zero. So this is F external is equal to F gravity. We have done similar kind of argument in work per energy when calculating work done by spring. Remember?
Yes, sir.
Yes, sir. This I understood.
So here, um, this is nothing but the work done in moving a unit case, 1 kg of mass, right? For 1 kg of mass, what is the gravitational force? Fg bar is equal to m times e bar. Here mass is how much? 1 kg. So that will be equal to how much? E bar. Is that right? So I can say that this is minus E bar dot ds bar. Now where is the value of electric field? The value of electric field is inward. Where is the value of dr? Dr is also inward. That means the dot
Inward.
positive and negative.
Negative only, sir.
Both of them are
Both of them will be.
Both are there are same direction, no, so it will be positive.
yes, it will be positive. So this will be E dr I can write.
Uh,
But what's the value of E? G. Capital M small m by r square. Right? That will be G capital M small m by r square times dr. That's a small work done in moving it from point O to point P. But we know that the gravitational potential is nothing but the total work done, right? Is a total work done in moving it from point A to, you mean, total work done in moving it from where infinity to point P. So I can put this as G capital M small m by r square dr. Clear? By r square dr. From where? From infinity to r.
Infinity to the R.
Here this will be minus integral. How much is this? G capital small m. Yes, this is G. Uh, we can take capital M small m common. G capital M small m. Integral 1 by r square. That will be how much? Minus 1 upon r.
Minus 1.
Since integral 1 upon r square dr, that will be equal to integral r power minus 2 dr. This will be integral. That means this will be r power minus 2 plus 1 by minus 2 plus 1. Limits from a to b. That means minus 1 upon r from a to b. Now from over here, what we can say, this will be minus g capital M small m by, let's substitute the limits. If we substitute the limits, this will be minus 1 by r minus of 1 by infinity. We know that 1 by infinity is how much? 0.
Yes, sir.
This here we have got this value as how much? G capital M small m by r. It says that this is the work done by external agent, but I definitely feel that there is some issue with the negative sign. 1 second. We have done it correctly only. work done by external force, done by external agent.
Sir, the value, the formula for E, won't it be G capital M by R square? Because it's force acting per unit mass, right?
Okay, the mass was supposed to be substituted as 1. So this is 1. This is gm by r square. Apart from that, we got an issue with negative sign.
Sir, if E bar and DS bar are in the same direction,
It
won't
should
it
be
be?
plus EDR, right?
Yes, sir, because minus E bar into minus DS
Into
bar would
minus
be
EDR.
plus EDR.
So what do you say that would be?
Plus EDR.
Why?
Because both are in the same direction, both are negative, no?
No, that's why the dot product of them became positive. This term became positive plus EDR. Then by external agent is equal to bar dot dr bar.
Sir, here V represents the gravitational potential.
I didn't get you.
V represents gravitational potential.
Yes, V represents gravitational potential.
Okay.
Here, maybe our mistake is that we were assuming that electric field is inward, but sorry, gravitational field is inward. So best thing to do would be, because we are substituting, however, substituting the value of limits. So it would be better that if we ignore the direction of E. Got the point? Let's assume that E is radially outward and then do the dot product. So and leave this the sign for the limits.
Okay, sir.
Did you understand the logic?
Because we are not considering the sign for DR also, right? It should be positive otherwise, sir, if we consider directions.
If you consider the directions,
It should be plus EDR.
if you
It should
consider
be plus EDR. Because we are considering directions also, or not also, it will be this plus DR.
so just take this is minus, let's put it as minus EDR. And this will become plus, 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 and a minus. Yes, this way it seems correct. You see, that's what I was quoting, that here a negative sign creates an issue. Is that right? Here, because we are taking the limits. Okay, these limits are also creating a problem over here. But look here. What we have done here is that we wanted the work done by external force. Work done by external force is nothing but magnitude wise equal to the uh, magnitude wise, they are equal to the work done by, I mean, external force, because it at an instant kinetic energy is zero. That means instantaneous velocity is zero. That means acceleration is zero. That means net force is zero. So external force must balance the internal force, or internal force and external force, they are equal. So we have written that external force is nothing but negative of the gravitational force. Clear? Now from that, we have said that because we know that the gravitational force is me bar. Here, mass is how much? 1 kg. Here, mass is how much? 1 kg. So we can say that this, if mass is 1 kg, that will be E. So that will be minus of minus E dr, and we got the work done. This is the work done in moving 1 kilo of mass by a small distance dr. That's the total work done in moving it from infinity to point P. Then substitute the limits as infinity to r. We get it as G capital M times integral of this will be minus 1 upon r from infinity to r. So Gm times minus 1 upon r, substitute the limits. This will be first substitute as small r, next you substitute as infinity. 1 by infinity is 0, so you can answer as minus Gm by r. Any confusion here?
So this is gravitational potential at a point above the Earth's surface.
Gravitational potential?
At a point above the Earth. surface.
Yeah, that means from at a particular height, you get this potential as minus g capital M by r, where m is the mass of the earth at a distance r.
Okay, sir.
So
This
I still have some confusion with the negative signs.
what?
Minus plus. I still have the confusion with that negative positive sign.
Okay, assume that electric field is radially outward. Here,
Sorry, sir.
here, what we have what you do is that ignore the direction of e bar, because basically in mathematics anything here the mistake what I've done was that I've pushed it inside. Okay, the proper derivation would have been correct had I taken it away. Okay, had I pushed it away, dr from inside to outside, because basically mathematics it always says that any value, if you are assuming any change, that must be positive change. That means it should increase. But here, because I assumed it assumed to be coming from outside, so I assumed that it is coming inside. But if you do it in this manner, look here. Uh, for till here, is it okay? This step
Yes, sir.
ds minus fg dot ds, is this okay?
Yeah, how did the minus sign come here also?
Here, this that external is equal to minus fg.
Yes, sir, we did this. Yes, understood. Yeah.
So from here, what I'll do, I'll rewrite this. Finally, I'll substitute the value of m. If not, I'll divide it. Is that okay? So we know that fg is equal to minus m. So fg is equal to me bar. Is that correct?
Yes, sir.
The bar is equal to me bar. Let's not substitute it as m. So this is minus m. I keep it out. Where is the direction of electric field? Electric field is inside.
Opposite to
Where,
that, E.
where is the direction of dr? Dr is outside. What's the angle made by them? Pi. That will be
Hi.
e dr cos pi. Cos pi will be how much?
Cos
Minus 1.
minus 1.
So this will be minus m e. I mean minus e dr, minus m minus e de. Sorry, minus e times dr. Is that right?
Yes, sir.
Minus of minus, that becomes how much? Plus m.
Plus.
Plus me dr. Clear? So now
Yes,
let's
sir.
substitute the value of m as how much? 1. Because we are
Right.
doing it, calculating it for 1 kilo of mass. Substitute it for 1. So what will you get? You'll get as plus e dr.
Plus medium.
Is it okay
Got
now?
it, sir.
And
Yes, sir.
I do realize my mistake. So in mathematics, always dr change means anything that is increasing. Here, because in gravity we were trying to pull it inside, so I took dr to be decreasing, but that was a mistake.
Okay,
But
sir.
the logic,
Scroll up a little. I want the diagram. Yeah, thank you, sir.
Karthik, this V is called the gravitational potential. There is nothing like universal gravitational potential. There is universal gravitational constant, which is G. But there's nothing like universal gravitational potential. This is what's called gravitational potential at point P, which is at distance r, from mass capital. Is it done?
1 minute, sir, just the last statement. Done, sir. So today are we having the doubt session?
If you people want, we can have it.
Yes, I sent my doubts yesterday, right?
Okay. So the same timings, 3:30 to 4:30.
Okay, sir.
Now coming to here, from this, what's the
Just
relation
1 minute,
between?
sir. I didn't complete it.
Okay. Is it done? Now look here. From this, overall, what's the relation over here? We can say if for m kilos of mass work done, okay, or what we could have simply calculated is, I mean, here whatever we have actually done is that we found that potential, okay, we can say that total potential is nothing but total work done by mass m. Here, that is nothing but integral f bar external dot ds bar, f bar external dot ds bar, f bar external dot ds bar by mass m from infinity to point p, which is the distance r, that is minus m times integral e bar dot ds bar, e bar dot ds bar from infinity to point r. Now you can cancel the value of m and we can simply say that this is minus integral e bar dot ds bar or dr bar, they mean the same thing, right? Because here we are moving in the radially outward direction. So this will be dr bar from infinity to r. So here from this we can claim that the relation between this is minus integral e bar dot dr bar from infinity to r. This is a relation between gravitational field and the gravitational potential. Now coming to here, if you want to make about some comments, if you want to comment on this gravitational potential, understood. So is the gravitational potential a scalar or a vector?
It is scalar, right?
Yeah, sir, because it's dot product, no?
Yes. So gravitational potential is a scalar quantity. It's a scalar quantity. Now next thing, does it depend on the path along which you brought the mass?
No, sir.
You see, since V is equal to G capital M small m by R with a negative sign, this is from infinity to point P. That means had you brought a block of mass m or mass 1 kg, understood, had you brought this 1 kg of mass from a distance, this is 1 kg of mass, 1 kg of mass from point O to point P, let's say this distance was r final, here you're bringing it inside, let's say this distance was r initial. If you remember, we have written this quantity as how much? Minus g capital M times 1 by r, we have written it as 1 by r minus 1 by infinity, right? That means here that was the potential at a point P which is at a distance r. Clear? But if you want to talk about the potential difference, delta V, that is final potential minus initial potential. That is final potential minus initial potential. That will be how much? Minus G capital M times 1 by R final minus 1 by R initial. Got the logic? So this is how you write about the change in potential. You see, this final potential depends only on, that is potential difference. This potential difference comma delta V. Since potential difference comma delta V depends only on potential difference or potential at a point. It depends only on the initial and final distances. Initial and final distances, and not on the path. Not on the path along which the mass was brought. Do you agree?
Yes.
Yes.
So irrespective of the path along which you brought it, understood? Irrespective of the path along which you brought it, the that means if you bring along straight line, or if you bring along any curved path, or from this particular point you take it to some other location, again you bring it back here. Still the potentially same. That is nothing but potentially same means work done will be same. Is that right?
Yes, sir.
Understood the logic? Now, in this case, let's say if you want to calculate in moving it from point O to point P, then how do you do it? Is that you multiply the mass which you are bringing times the potential difference. So this will be minus G capital M small m by 1 by R final minus 1 by R initial. Most of the times, in case of work done by external agent, the work done by external agent is negative. That means we are not actually doing work. Who is doing the work? The gravitational field itself is doing the work. That means if the even the gravitational field is a conservative field, so if conservative field is doing the work, what must happen to its potential energy? Its potential energy must increase or decrease.
Increase.
Let's see. We know that since work done by external agent is equal to change in potential gravitational potential energy, so this is nothing but minus G. That was supposed to be how much? U final minus U. Yeah, this will be minus G capital M small m.
Sir, isn't M delta V?
Here, what?
Isn't it M delta V?
Yes, M delta V. So delta V, it's minus G capital M 1 by R final minus 1 by R initial. I multiplied it with
No,
small m.
W external.
What?
W external.
And
M
this is
delta V, no sir.
yes, correct only.
No, here in the bottom part, W external you have just
This
written
is
it.
the work per energy. Since delta K is equal to 0.
Achha, this is delta U.
Yes, delta U, potential energy.
Okay.
Since work done by external agent is equal to change in kinetic energy plus change in potential energy. But change in kinetic energy in the given case is how much? 0. Clear? Change in kinetic energy 0. So that is U final minus U initial is equal to this much. Now what we can say is that if since work done by external agent in this case is, I meant to say, while bringing it to point P, work done by external agent is negative, work done by, so what must happen to the potential energy? Potential energy must decrease. Clear? So here, from O to P, work done by external agent is negative. This implies change in potential energy is negative. That is, final potential energy is less than initial potential energy. Why? Since work done by gravity is positive, so that means energy is lost by the gravitational field. That means whatever energy, gravitational potential energy was stored, that is being lost in the form of work done. Did you get the point? Whereas if you move it from point P to point O, then what will happen? Work done by external agent will be positive. So there will, you are doing work against the system. So that means what will happen? Its energy will increase. Here what? Why? Because the work done by gravity is negative. Understood the logic? Now we know that is delta U. Delta U is nothing but U final minus U initial. U final minus U initial is equal to minus G capital M small m by 1 by R final minus 1 by R initial. So from this we can say that gravitational potential energy at any point is equal to how much? Minus G capital M small m by R. This is a gravitational potential energy. Gravitational potential energy. If you remember, I think I've used this expression to show that in daily life, whatever uh, from this only we found that the gravitational potential at a height h is mgh. Remember? Do people remember that? I think you have forgot.
Sorry, sir.
So here, as r initial tends to infinity, u initial tend to 0. That means this is taken as the reference potential. There. That means what we do is that we assume that if this is a block of mass m, if this is a block of mass m, and initially the mass is over here now, whereas initially it was at infinity. Understood? Let's say this block of mass m was at infinity. At infinity, the initial gravitational potential energy. This is what R initial. R initial is tending to infinity, right? R initial is tending to infinity. So this is minus G capital M small m by R initial. R initial is tending to infinity. So overall value will tend to 0. So this we take it as a reference potential.
Yes.
Now, with respect to that, when you bring it into the vicinity of block M of mass M, supposed to be capital M. Now, if you bring it to a point P, which is at a distance R, let's say R final is equal to R, then we say the final potential energy is equal to minus G capital M small m by R final. So that is minus G capital M small m by R. So always we take the reference potential to be 0. So with respect to that, we talk about gravitational potential energy at a point which is at a distance r. If separation, if there are two masses, capital M and small m, and if the separation between them is r, then the potential energy at any point, okay, the potential energy for a separation r is how much? Minus G capital M small m by r.
So could you scroll up a bit?
Sure. In fact, here also we can tell work done is equal to total work done by mass, or we can also say that work done is equal to mass times potential. This is one very nice relation.
Sir, on the right side, when you calculated the expression for gravitational potential energy, wow, I didn't understand the part where you took m delta v, sir.
M delta V. Work done in moving point point O to point P. That should be mass times potential difference, right? You see,
I didn't get you.
work done in bringing, let's say you brought and placed the mass directly at point P, then that is work done is mass times delta potential at point P. Is that okay?
Yes, sir.
Work done in bringing O, that will be mass times potential at O.
Yes, sir.
Let's say that means you directly brought it and placed at point P. The work done is, for bringing it and placing at point P, the work done is how much? This bringing and placing it here, it is WP. Bringing it and placing here, that is WO. But while for shifting this, can I assume that this is WP OP or delta W work in moving from O to P? Can I say that work done in moving from O to P, because it doesn't depend on the path? I'll say that work done at point P minus work done at point in placing, bringing the block to point O. Do you agree with that?
Yes, sir.
That will be mass times potential at P minus potential at O.
Mass times delta V. Okay, sir.
Understood? This is mass times
Yes, sir.
G capital M small m, sorry, G capital M, uh, sorry, yeah, this is mass times minus G capital M by 1 by R final minus 1 by R initial. That's the expression. That's what I've written. Is it visible now? Such small font?
It's fine, sir. So could you move up a little bit? So would you scroll down a bit? So this U equal to minus G capital M small m by R is gravitational potential energy at a point. No, sir.
Yes, at a point. At a point means if both the masses are placed at a separation R, then that is the gravitational potential energy.
Okay, sir. So could you once explain these two bits, sir, from O to P and from P to O? How did you determine how they are negative and positive, the work done in potential?
You see, because gravity itself is pulling it towards the block M. So in that case, work done by external agent will be negative because we did not do any work. Even if you just place this mass,
Okay, sir.
it itself will pull it. We did not do any work. But while taking it away, because gravity will be
We
trying
are
to pull it
doing
in,
work against the gravity.
yeah, we have to work against the gravity. So work done will be positive in that case.
Okay, sir.
Are you done copying?
Yes, sir.
So we'll conclude today's class over here. So in the afternoon at 3:20, we'll discuss doubts if you have any.
Yes.
3:20 or 3:30. Thank you.
Thank you, sir.
Thank you, sir.
Sir, so you have sent the rotation I told you yesterday also.
I've sent right.
Yeah, so sir sent it on the group.
Sir, sent. Okay, okay. I didn't check. Sorry, sir.